In this video, we'll quickly go over some definitions again, and we're going to balance reactions using oxidation numbers, and more importantly, we're going to balance reactions in acidic solutions. We introduced some key redox terms in our last video, but let's go over them again. As we remember, reduction is a chemical process that involves a gain of electron. Whatever species is being reduced gains electrons. Its oxidation number will decrease or get more negative. Or on the other hand, oxidation is a chemical process where there is a loss of electron. Whatever chemical species would be losing electrons, and the oxidation number would be increased or getting less negative or more positive. So a common reduction reaction would be the reaction of chlorine, or the conversion of chlorine into two chloride ions. Initially, the oxidation number for chlorine, Cl2, is 0 because it is a neutral molecule. However, at the end of the day, chlorine becomes chloride. It's now a negative ion. It's an anion, and it's -1. So each atom or each ion is now -1. The oxidation number went from 0 to -1. It got more negative. So therefore, this is a reduction reaction. On the other hand, we could have something like a sodium metal, neutral, becoming a sodium ion. Here we have oxidation a number of 0 for a sodium metal because it's neutral. And because an ion, it's a cation, becomes +1. The oxidation number is now +1. So the oxidation number went from 0 to +1. It increased, therefore, as an oxidation reaction. A couple more terms that we need to review. A reduction agent or a reducing agent is something that causes a reduction by donating electrons to something else. A reduction agent or a reducing agent gets oxidized itself because it gains an electron. On the other hand, oxidizing agent, they themselves get reduced, but they help something else get oxidized. The analogy we used last time was an agent of a travel agent. A travel agent doesn't actually do the traveling, but it helps you in the traveling. So it's important to remember that reducing agent gets oxide itself, whereas an oxidizing agent gets reduced itself. In picture form, we have these definitions restated now. Here we have compound A. It currently has 2 electrons. However, at the end of the day, as a product, it has no electrons. There's missing electrons here. Therefore, compound A lost electrons, and remember OIL, oxidation is the loss of electron. On the other hand, compound B gained electron. It initially had no electron, but now it has electrons. Compound B gained electron, and remember RIG, R-I-G, reduction is gain. So now compound A got oxidized, compound B got reduced. Because compound A got oxidized, it's the reducing agent. It helps something gets reduced. Who did it help? It helped compound B get reduced. On the other hand, compound B is called the oxidizing agent. Itself gets reduced, but it helps compound A gets oxidized. Now, with our understanding oxidation number and those terms, we can now dwell further into electrochemistry. Electrochemistry really is about the transfers of the electron. By using oxidation number, we can predict or even determine whether or not an electron transfer has occurred. If the oxidation number of an atom or an ion changes, then we know electron has been transferred. Therefore, we can call this a reduction-oxidation reaction or a redox reaction. However, if the oxidation number of an atom or an element does not change when it goes from a reactant to a product, there is no transfer of electrons. It is not a reduction-oxidation reaction. Therefore, it's not a redox reaction. And again, a quick review. An increase in the oxidation number is defined as an oxidation, whereas if the oxidation number decreases, it is a reduction. It's a decrease in oxidation number because you gain electrons and the electrons are negative. So if you get more negative, it's a reduction. If you get more positive, it's a oxidation. We can cement the concept of redox chemistry by looking at the combustion of coal, which is mostly carbon, with a reaction with oxygen to produce carbon dioxide. Now the oxidation number for carbon is 0 because carbon itself is neutral. For the oxidation number for oxygen, it's also 0 because oxygen itself is neutral. However, in carbon dioxide, we can now go back to our oxidation number determining rules. Oxygen is always going to be -2. So in order for carbon dioxide to be a neutral molecule, we have one molecule or one atom of carbon. We don't know what that oxidation number is yet. And 2 plus 2 times -2. And the entire molecule, carbon dioxide, is 0. So if we were to solve for x, we can find out the x is +4. Or in this case, the oxidation number for carbon is +4. So therefore, the oxidation number of carbon went from 0 to 4, and because it got more positive, this is carbon, we can say got oxidized. On the other hand, the oxidation number for oxygen went from 0 when it was in O2, neutral molecule, to -2 in carbon dioxide. It got more negative, it gained electrons, and gaining electron we say is a reduction. So oxygen got reduced, whereas carbon dioxide got oxidized. Okay, let's get to the meat of the matter. We're to balance redox reactions using oxidation numbers. The first ones we're going to do are for acidic environment. Acidic means that we're going to add H+ to either the reactants or the products to help us balance the equation. The example here we have methanol plus MnO4 permanganate ions yielding manganese ion and formaldehyde, CH2O. And the question tells us this is an acidic solution. Now to solve this, there are many steps, and I encourage you to pause the video every so often and record or write down these steps. Alright, so step 1 is to assign oxidation number and identify the atoms or ions where the oxidation number changes. So it might take a few minutes, but you should go through the entire reactants and the entire products to determine the oxidation number of all the elements. So in methanol, the carbon is -2, hydrogen is +1, oxygen is -2, and again hydrogen is +1. In permanganate, manganese is +7, oxygen is -2. Those are the oxidation numbers of our reactants. Let's look at the products now. Mn2+, that's simple because the ion itself is 2+, so the oxidation number for manganese is +2. And CH2O, well, we have to determine that, or we have to remember that the oxidation for hydrogen is always +1, and the oxidation number for oxygen in a compound is -2. And then if we're to have a neutral molecule for formaldehyde, here the oxidation number for oxygen must be 0. Looking at the oxidation numbers we did, we can see that the oxidation number for carbon went from -2 to 0, and we'll do this in white here, the oxidation number for manganese went from +7 to +2. The oxidation number for hydrogen, -1, and oxygen, -2, did not change from the reactant side to the product side. So we know that hydrogen and oxygen is not involved in the transfer of electrons here in this example. Our next step is to determine the change in the oxidation number, and using that determine the number of electrons transferred per atom. So we said before that carbon went from an oxidation number of -2 to 0. It got more positive by 2. And this is the change in oxidation number is per atom, or in this case per carbon. On the other hand, we have manganese, Mn. It went from +7 to +2. Its oxidation number went down by 5, and again this is per manganese ion. So we know that the carbon, we can say, lost 2 electrons here because its oxidation number went up by 2, whereas manganese gained per atom 5 electrons per atom because its oxidation number went down by 5. The next step, after we determine the number of electron change per atom, is to determine the number of electrons transferred per molecule of reactant. Now, in the last step, we just said that there's per atom of carbon, there's 2 electrons transferred. However, in the formula for methanol, there is the invisible subscript of 1 there, 2 electrons per carbon, but there was only 1 carbon, so we know that there is 2 electrons transferred per molecule of methanol. On the other hand, we know that the each Mn manganese ion gains 5 electrons, and the invisible subscript here is again the 1, so that each molecule of permanganate, MnO4, there is going to be 5 electrons transferred. Now, in this case, it worked out that for us, the subscript, is the magical invisible number of 1. However, it may not be the subscript 1. For example, the molecule dichromate, Cr2O7, the subscript here for chromium is 2. So therefore, you would have to multiply whatever number of electrons per chromium, Cr, multiply that by 2 to determine the number of electrons transferred per dichromate, Cr2O7. Once we've determined the number of electrons transferred per molecule of the reactant, we have to determine how many molecules of each reactant do we need in our reaction. But first we have to do a little math. We have to determine the lowest common multiple of the number of electrons that are transferred in this reaction. We know that for methanol, there's going to be 2 electrons transferred per molecule, and for permanganate, MnO4, there's going to be 5 electrons. So the lowest common multiple between 5 and 2 is 10. That means that in this reaction, there will be 10 electrons gained, and on the same hand, there will be 10 electrons lost. Well, how are you going to get 10 electrons from methanol? Well, because we know each methanol molecule loses 2 electrons. To get 10 electrons in total, we have to multiply this by 5. So the coefficient for methanol is 5. On the other hand, because we know each molecule of permanganate, MnO4, gains 5 electrons, and to gain a total of 10 electrons, we're going to need 2 molecules. So the coefficient that goes in front of MnO4 is 2. Our next step is relatively straightforward. Our sub-step is to balance the reactants and products. So now, because we have 5 carbons on the left, we need 5 carbons on the right, and the only way to do this is to put a 5 in front of the formaldehyde, CH2O, and then to balance the Mn, we have to put a 2 in front of the manganese ion. In order to balance out the O's and the H, we're going to leave that for our next step. Yep, that's right. We don't need to fully balance the reactions just yet. We just have to balance the chemicals that are directly involved in the redox reaction. The elements that either gain an oxidation number or lost in oxidation numbers. So now we're on to step 5, and it tells us to balance the oxygen atoms by using water. We can add water to either the product side or the reactant side. After we do that, we can then balance hydrogens using H+ ions. So let's continue on with our example. First, let's determine the number of oxygen on the reactant side. We have 5 times 1, so that's 5 oxygen. 2 times 4, that's 8. 5 plus 8 is 13. So we have 13 oxygens on the reactant side, and we're going to need 13 oxygens on our product side as well. Well, right now, let's check how many do we have. There's no oxygens here, and here in the formaldehyde molecule, there's 5 times 1, or 5. So we're going to need 8 more oxygens on the product side, and the way we do that is by adding water molecules. So we're going to add 8 water molecules on the product side. Now that oxygen is balanced, we're going to balance hydrogens. Again, let's go back to our reactant side. We're going to use red now. We have 5 times 4, or really 20 hydrogens, and there's no hydrogens in permanganate, MnO4, so 20 plus 0 is 20. So on the product side, let's determine the number of hydrogens. Again, there's no hydrogens here. Here there's 5 times 2, or 10, and now with our newly added water, we know there's 8 times 2, or 16. 10 plus 16 is 26. So it appears that we are going to be short 6 hydrogens on the reactant side because we only have 20 on the reactant side and 26 hydrogens on the product side. So how can we fix that? We can simply add 6 H pluses to the reactant side. So the key to balancing O's is to add water to either the reactant side or the product side, and the key to balancing hydrogens is to add H pluses to, again, either the reactant side or the product side. Now that we have our atoms balanced, let's double check to make sure all the charges are balanced as well. On the reactant side, we have here 6 positive, and here 2 times negative 1 is negative 2, so 6 plus minus 2 is positive 4 on the reactant side. And charges here, we have 2 and times positive 2 plus 4, and all the other molecules are positive. So yes, we have a balanced reaction in terms of charges, positive 4 on the left and positive 4 on the right. So now that we've fully balanced our reaction in terms of both atoms and charges, let's go back and see which entity got reduced and which entity got oxidized. Here we can see that the oxidation number for carbon went from -2 to 0, so it lost electrons, so it got oxidized. Whereas on the other hand, the manganese in permanganate went from positive 7 to positive 2. It got less positive or more negative. It gained electron, so manganese itself got reduced. Let's look at another example. Here it is the reaction of hydrogen sulfide, which is toxic, with oxygen and gas to produce sulfur dioxide, which is less toxic, and water vapor. Again, the first step is to determine the oxidation number of all the elements in our reactants and our products. Here, remember, hydrogen is positive 1, and then sulfur, because to maintain a neutral molecule, has to have an oxidation number of -2. Oxygen, being a neutral molecule, has an oxidation number of 0. Now let's look at the product side. Oxygen, when it's in a compound, has an oxidation number of positive or -2. And to make everything all balanced, sulfur has to have an oxidation number of positive 4 in SO2. And again, in the molecule, oxidation number of oxygen is -2. And to make everything balance out, hydrogen have to have an oxidation number of positive 1. Our next step is to determine which element is gaining electrons and which element is losing electron. Here we have sulfur going from -2 to positive 4. It is losing electrons, and it's being oxidized. And for oxygen, it is going from 0 to -2 here. It is being reduced. It is gaining electrons. However, that only tells us the number of electron transfer per atom. Going from -2 was positive 4 is gaining 6 electrons, or losing 6 electrons. And for oxygen is 2 electrons per atom. But remember, we have to determine the total number of electrons per molecule, not just per atom. Now in H2S, there's only 1 atom of sulfur, so the number of 6 electrons per molecule remains the same. But in O2, because of the 2, there is now 4 electrons transfer O2 molecule. So sulfur in hydrogen sulfide loses 6 electrons per molecule, and oxygen gains 4 electrons per molecule. Now that we've determined the number of electrons gained or lost per molecule of the reactant, we have to determine the lowest common multiple. And the lowest common multiple between 4 and 6 is going to be 12. That means that we have to, in our reaction, when we're balancing, we need to produce 12 electrons coming from hydrogen sulfide, and to get that, we need to multiply the molecules of hydrogen sulfide by 2. On the other hand, for oxygen, it needs to absorb 12 electrons in total. The only way we can get 12 electrons is to multiply everything by 3. So the coefficient is 3 for O2 on the reactant side. And then to balance out our products, we just need to look at the number of sulfur atoms. Here we can balance everything by putting a 2 in front of SO2, because there should be 2 atoms of sulfur on the product side, and we can put a 2 here in front of water because in total now there's going to be 6 atoms of hydrogens on the product side. In this example, we do not need to add water to either the reactant side or the product side to balance out the oxygens, and further, we do not need to add hydrogens to either the reactant side or the product side to balance out the number of hydrogens.